250 million years ago, Earth entered one of the most unstable periods in its history. The balance that sustains climate and life began to falter. The oceans slowed. Circulation patterns that had once carried oxygen through the depths weakened, and more than 90% of marine species disappeared from the fossil record. Entire reef systems vanished. Forests collapsed across continents, joined together in the vast supercontinent of Pangaea, where deserts stretched deep into the interior and seasons grew severe. Global temperatures rose by 8 to 12 degrees as immense volcanic eruptions released carbon into the atmosphere for hundreds of thousands of years. Oxygen levels fell below what large animals could endure. Scientists believe some regions may have reached lethal wet bulb heat conditions, while parts of the oceans turned toxic, releasing gases that altered the chemistry of air and sea. The carbon cycle slipped out of balance. Evidence preserved in ancient rock layers reveals abrupt isotope shifts, signals of a biosphere under extreme strain. Recovery would not come quickly. It would take millions of years for ecosystems to rebuild, guided by plate tectonics, ocean buffering, and the fragile conditions that allow stable liquid water to persist. But how close did Earth come to crossing a planetary threshold it could not reverse? What separates a world that recovers from one that becomes permanently sterile? How did the delicate balance of atmosphere, oceans, and magnetic shielding hold when so much else collapsed? And could the same forces that transformed Mars once have nudged Earth toward a similar fate? Tonight, we follow the geological traces of a crisis that nearly altered our planet's destiny. But before we begin, if you're already enjoying this moment of wonder, it would mean a lot if you gave this video a gentle like or subscribed for more sleepy science journeys like this. And if you don't mind, tell me in the comments where in the world you're watching from tonight and what time it is there. It's always a joy to see how far across our planet these sleepy science videos drift. So now take a deep breath, let your shoulders relax, and together let us drift into the time when Earth almost became a barren world. Far from the warmth of our oceans, another world circles the same sun under a far thinner veil of air. Mars carries an atmosphere composed mostly of carbon dioxide, yet it is so sparse that surface pressure amounts to only a fraction of Earth's. The gas that on our planet can trap warmth there drifts in a tenuous sheet, offering little insulation against the vast cold of space. Daylight reaches the ground without the buffering thickness that softens temperature on Earth, and heat gained under the sun escapes almost as quickly as it arrives. Under that fragile sky, stable liquid water cannot persist across open ground. Any ice exposed to sunlight tends to sublimate directly into vapor, while transient melt would boil at temperatures that on Earth would still feel bitterly cold. What water remains lies locked in polar caps or hidden as frozen reserves beneath the soil. Yet orbital imagery and rover explorations reveal winding valley networks, layered sediments, and mineral traces that form in the presence of water. Long ago, rivers carved channels and lakes gathered within impact basins, leaving behind the quiet geometry of ancient shorelines. The present Martian surface endures dramatic thermal swings. With little atmospheric mass to retain warmth, temperatures can rise modestly in equatorial daylight and then plunge far below freezing after sunset. Dust storms, sometimes planet-encircling in scale, sweep across plains stripped of vegetation and oceans, redistributing fine particles beneath a salmon-colored sky. These storms obscure the sun, but do not provide the kind of sustained climatic moderation that oceans and thick air create on Earth. Deep within its interior, Mars cooled more rapidly than our larger planet. Geological evidence suggests that its once active core dynamo faded billions of years ago, weakening the global magnetic field that had shielded the upper atmosphere. Without that protective envelope, solar wind particles gradually stripped away lighter gases, thinning the atmosphere further with each passing epoch. Gravity, lower than Earth's, offered less resistance to this slow escape. Over immense spans of time, atmospheric molecules were carried off into space, and with them the pressure needed for long lived surface water. The contrast reveals that habitability rests not on a single ingredient, but on a balance among many: atmospheric thickness, magnetic shielding, internal heat, gravity, and the presence of liquid water interact in subtle feedbacks that stabilize or erode a world's potential for life. Mars preserves the record of having once approached that balance, then drifting away from it. In its dry channels and oxidized dust, the memory of a wetter era endures, a reminder that planetary conditions are neither fixed nor guaranteed, but the outcome of intertwined processes unfolding over deep time. Not every world that forms within a gentle orbit keeps the conditions that allow life to persist. Planets begin with fire, collision, and volatile escape, yet only a few settle into long eras of equilibrium. Earth did not inherit stability as a permanent gift. Its balance emerged from interacting systems that continually adjust, compensate, and renew. The fragile recipe for life is not a single ingredient, but a network of processes that lean against one another in quiet tension. A stable atmosphere rests at the center of this balance. Gases circulate, absorb energy, and redistribute heat across latitudes, softening contrasts between equator and pole. Nitrogen forms the bulk, providing inert mass that sustains pressure, while smaller concentrations of carbon dioxide and water vapor regulate temperature through radiative exchange. Too little greenhouse effect, and oceans would freeze from edge to edge. Too much, and heat would accumulate beyond the tolerance of complex organisms. The thickness of this gaseous envelope, held by gravity and replenished through volcanic outgassing, allows liquid water to exist within a narrow thermal window. Thread through the air is the carbon cycle, a planetary conversation between rock, ocean, and life. Carbon moves from atmosphere to sea, from sea to sediment, from sediment into the mantle, then back again through volcanic release. Rainwater reacts with exposed silicate rocks, drawing carbon dioxide from the sky and storing it in mineral form. Rivers carry these dissolved materials to the ocean, where they become part of limestone seafloors. Over immense spans of time, plate tectonics returns portions of that buried carbon to the atmosphere, maintaining a long rhythm of balance. When temperatures rise, weathering accelerates, gradually lowering atmospheric carbon dioxide and moderating warmth. When temperatures fall, the process slows, allowing greenhouse gases to build once more. Beneath continents and ocean basins, plates of lithosphere drift atop the convecting mantle. This movement reshapes coastlines, builds mountain ranges, and continually recycles crust. It also renews chemical gradients that support climate regulation. Subduction carries carbon-rich sediments downward, while mid-ocean ridges create new crust that interacts with seawater in hydrothermal systems. Without active tectonics, carbon burial and release would stall, and climate could drift toward extremes without correction. The oceans act as vast reservoirs of heat. Water requires significant energy to change temperature, and this capacity buffers seasonal and long-term fluctuations. Currents transport warmth from tropical regions toward higher latitudes, redistributing solar energy and stabilizing atmospheric circulation. Marine chemistry also absorbs large quantities of carbon dioxide, tempering atmospheric spikes and linking biological productivity to global climate. The interplay between ocean circulation and atmospheric patterns forms a dynamic equilibrium that dampens abrupt change. Above it all, Earth's magnetic field deflects charged particles streaming from the sun, generated by motion within the liquid outer core. This field shields the upper atmosphere from direct erosion. Over geological time, such protection has helped preserve atmospheric mass and maintain surface pressure compatible with liquid water. Together, these systems create long-term climate stability, measured not in centuries, but in millions of years. Stability does not imply stillness, only resilience within limits. Earth's balance is rare because it depends on planetary mass sufficient to retain gases, internal heat that persists long enough to drive tectonics, a protective magnetic dynamo, abundant surface water, and chemical feedbacks that moderate extremes. Remove or weaken one element, and the others strain to compensate. Life endures here not by accident alone, but through the steady interplay of forces that quietly sustain a habitable world. Before instability announced itself in stone and sky, the planet had gathered its continents into a single immense landmass. Pangaea stretched from pole to pole, an unbroken sweep of terrain, surrounded by the global ocean Panthalassa. Along its margins, waves moved against long, curving coastlines, but deep within the interior, the sea lay impossibly far away. Mountain belts stitched together the seams of earlier collisions, and broad basins collected sediments under an open horizon. The geography alone shaped climate into patterns unlike those of the present world. Distance from the moderating influence of ocean water left the continental heart exposed to extremes. Summers grew intensely hot beneath an unfiltered sun, while winters cooled sharply across high-latitude plateaus. Rainfall struggled to penetrate far inland, creating wide desert belts where dunes migrated slowly across arid plains. Seasonal contrasts intensified because a single supercontinent disrupts atmospheric circulation, altering the pathways of winds that might otherwise distribute moisture. Yet along coastal regions and in certain upland zones, monsoonal systems formed, delivering intervals of heavy rain that fed river networks draining toward shallow epicontinental seas. Those seas spread across low-lying continental shelves, forming warm, sunlit platforms that fostered intricate reef systems. Sponges, rugose corals, bryozoans, and calcareous algae constructed layered frameworks of limestone that accumulated over millennia. Within these reef complexes lived brachiopods, ammonoids, crinoids, and early bony fishes, weaving food webs of remarkable complexity. The water column above supported plankton communities that formed the base of marine productivity, linking microscopic photosynthesizers to larger predators cruising the open waters. Sediments settled gently through clear shallows, preserving shells and skeletal fragments in quiet accumulation. On land, ecosystems displayed similar diversity. Amphibians lingered near lakes and river margins, while synapsids and early reptiles roamed floodplains and forested lowlands. Some lineages bore sail-like structures along their backs, possibly regulating temperature beneath fluctuating skies. Seed ferns, conifers, and other gymnosperms formed extensive woodlands in regions where moisture allowed sustained growth. Insects moved through these habitats in abundance, occupying ecological niches that ranged from detritivores to aerial hunters. The biosphere had expanded into a mosaic of communities adapted to varied environments across the unified continent. The climate system of the late Permian appears to have operated in relative stability, though it rested within boundaries shaped by geography and atmospheric composition. Carbon dioxide concentrations exceeded those of later eras, sustaining warmth that limited polar ice. Ocean circulation patterns redistributed heat across latitudes, and chemical feedbacks within weathering and sedimentation quietly regulated atmospheric balance. Stability did not imply calm uniformity, but rather an equilibrium maintained through interacting processes. Seasonal droughts, regional storms, and localized sea level shifts unfolded within predictable limits that life had adapted to over millions of years. Beneath this apparent steadiness lay subtle tensions. A supercontinent alters mantle convection beneath it, insulating the interior and influencing volcanic provinces that may one day awaken. Arid interiors accumulate organic matter differently than humid coasts, modifying long-term carbon storage. Shallow seas depend on narrow temperature ranges and chemical balances that can shift when circulation patterns change. None of these pressures announced catastrophe on their own. They formed a background hum within Earth's systems, a reminder that even periods of flourishing diversity rest upon dynamic foundations. In that late Permian world, life thrived across land and sea, sustained by balances that had endured, yet never remained fixed. Long before collapse etched its deepest mark into the fossil record, the signals began as quiet deviations, measurable only in stone and chemistry. Layers of sediment, accumulating across distant basins, preserved faint alterations in temperature and composition, as though the planet's steady rhythm had shifted by a fraction. Nowhere did the surface announce immediate catastrophe. Instead, subtle warming trends crept across both land and sea, detectable in the ratios of oxygen isotopes locked within microscopic shells. These ratios, sensitive to temperature, recorded oceans that were gradually absorbing more heat than before. The change was not abrupt, yet it persisted, decade after decade in human measure, millennia in geological time. As warmth increased, seawater chemistry responded. Dissolved oxygen levels began to decline in certain basins, particularly where circulation was already sluggish. Warmer water holds less oxygen, and as surface layers heated, stratification strengthened, limiting the vertical mixing that renews deep currents. Nutrients accumulated unevenly, altering patterns of productivity. In some regions, trace metals indicative of reducing conditions appeared more frequently in sediments, suggesting that patches of the ocean floor were slipping toward oxygen scarcity. These were localized disturbances at first, forming scattered mosaics rather than global uniformity. Within reef systems and shallow marine environments, biological communities responded to these chemical adjustments. Fossil assemblages reveal that some species disappeared earlier than others, long before the final extinction pulse that would later define the boundary. Certain brachiopods, foraminifera, and reef builders decline in abundance within specific strata, replaced by more tolerant forms. These early extinction pulses appear episodic, punctuating the record as brief downturns followed by partial recoveries. Such fluctuations suggest ecological stress accumulating in waves, as though environmental thresholds were being tested repeatedly. Carbon isotopes tell a parallel story. In carbonate rocks formed during this interval, the ratio between lighter and heavier carbon shifts abruptly in several sequences around the globe. This anomaly reflects a disturbance in the carbon cycle, a rapid injection or redistribution of carbon that altered the balance between reservoirs. Organic carbon burial, volcanic release, and methane input all leave distinct signatures within these isotopic excursions. The signal does not remain stable. Instead, it oscillates, indicating a system that had begun to fluctuate more widely than before. Terrestrial deposits also preserve hints of strain. Fossil pollen and plant spores show subtle changes in diversity and distribution. Some species that once flourished across broad latitudes become restricted to narrower ecological zones. Sedimentary layers record intervals of increased erosion, perhaps linked to shifting rainfall patterns or vegetation loss in vulnerable regions. River systems deposited coarser materials in certain basins, implying altered hydrology that carried sediments more forcefully downstream. None of these records alone conveys imminent global collapse, yet together they form a pattern of mounting instability. The first signs of disruption were therefore dispersed, embedded in geochemical proxies and paleontological details rather than in dramatic die-offs. Earth's climate system had not yet crossed its most critical thresholds, but feedback loops were tightening. Slight warming influenced ocean stratification. Stratification reshaped oxygen distribution. Oxygen stress altered ecosystems. Biological shifts influenced carbon cycling. Each adjustment fed gently into the next, creating a network of interactions that magnified incremental change. What appears modest in isolation reveals its significance when traced across continents and basins where the rock record aligns in quiet testimony. The planet remained inhabited, its biosphere still diverse, yet the stability that had endured was beginning to waver, almost imperceptibly, beneath the surface. In the far northern reaches of Pangaea, beneath landscapes that would one day be called Siberia, the crust began to fracture along immense lines of weakness. From deep within the mantle, buoyant plumes of molten rock rose slowly upward, gathering beneath the lithosphere until pressure could no longer be contained. What followed was not a single explosion, nor a brief season of eruptions, but the opening of vast fissures that poured lava across the surface in volumes rarely matched in Earth's history. Sheets of basalt spread outward in successive flows, each layer cooling and solidifying before being buried by the next. Over time, these flood basalts accumulated to thicknesses measured in kilometers, covering an area comparable to a continent. Millions of cubic kilometers of lava emerged from the interior, reshaping terrain and altering atmospheric composition in ways that extended far beyond the eruption sites themselves. The land did not erupt in isolated peaks, but along linear fractures that released molten rock like rivers of fire, advancing across plains and filling depressions with dark stone. The duration of this activity defies ordinary scale. Radiometric dating indicates that major eruptive pulses unfolded over hundreds of thousands of years, with some phases particularly intense and others quieter yet persistent. Each surge injected gases into the atmosphere, and between surges, cooling crust continued to interact with groundwater and organic rich sediments beneath the surface. The boundary between magma and sediment became a zone of chemical transformation, where heat-baked coal seams and evaporite deposits, liberating additional carbon and sulfur compounds into the air. Carbon dioxide released during these eruptions entered the atmosphere in sustained pulses. Unlike ash, which settles relatively quickly, carbon dioxide accumulates and lingers, altering the radiative balance of the planet. As concentrations rose, more outgoing infrared energy was absorbed and re-emitted downward, gently amplifying surface temperatures. Sulfur gases accompanied this release, forming aerosols that could temporarily reflect sunlight and induce short-term cooling. Yet the longer-lived greenhouse effect of carbon dioxide persisted beyond these transient veils. The climate response, therefore, unfolded as a complex interplay of warming and fluctuation, with cumulative heat gradually outweighing episodic cooling. The geological scale of the Siberian Traps becomes clearer when considering their remnants today. Eroded plateaus and layered cliffs record the stacked basalt flows, each a frozen chapter of prolonged effusion. Beneath these surface formations lie intrusive sills and dikes that once channeled magma upward, extending deep into sedimentary basins. Geochemical analyses of these rocks reveal isotopic signatures consistent with mantle-derived magma interacting with crustal materials, reinforcing the connection between volcanism and atmospheric change. As volcanic carbon entered circulation, it joined the broader planetary cycles previously described, yet at a pace that strained their moderating capacity. Weathering and ocean absorption continued, but the rate of input exceeded the rate of removal. The imbalance accumulated gradually across generations of flow, raising global temperatures and influencing ocean chemistry far from the eruption fields. What began as internal mantle dynamics manifested at the surface as altered climate, demonstrating how deeply Earth's interior processes can shape the conditions of life. The Siberian Traps were therefore not only a regional volcanic province, but a planetary force, their eruptions extending influence through atmosphere and ocean. Basalt plains hardened in silence after each flow, yet the gases they released remained active, circulating through air and sea, subtly redefining the balance that had long sustained the late Permian world. Carbon released from the northern flood basalts did not disperse and vanish. It lingered, accumulating in the atmosphere in pulses that overlapped and reinforced one another. Each eruptive phase added more carbon dioxide to a sky already adjusting to previous injections, gradually thickening the greenhouse blanket encircling the planet. Unlike ash or sulfur aerosols that settle or wash out over shorter intervals, carbon dioxide persists, cycling slowly between air, ocean, and rock. As concentrations climbed, the balance between incoming solar radiation and outgoing infrared heat shifted almost imperceptibly at first, then with growing consequence. Global temperatures began to rise beyond the subtle fluctuations recorded in earlier strata. Surface waters warmed, expanding slightly as they absorbed heat. On land, seasonal contrasts intensified under a strengthened greenhouse effect. Climate models constructed from geochemical evidence suggest an increase measured in several degrees across the globe, enough to push many regions beyond the range to which local ecosystems had adapted. The warming did not occur uniformly. Continental interiors experienced amplified extremes, while coastal margins faced altered rainfall patterns shaped by changing atmospheric circulation. As heat accumulated, feedback loops awakened. In high-latitude regions and within subsurface sediments, deposits rich in frozen organic material began to destabilize. Though true permafrost in the modern sense differed in configuration, analogous reservoirs of carbon lay locked within soils and shallow marine clathrates. Rising temperatures destabilized methane hydrates embedded in continental shelf sediments, allowing methane to seep upward into the water column and, in some cases, escape into the atmosphere. Methane, a potent greenhouse gas, absorbs infrared radiation more efficiently than carbon dioxide over shorter timescales. Even modest releases could amplify existing warming, reinforcing the trend initiated by volcanism. This amplification did not unfold as a single explosive release, but as a cascading sequence. Warmer oceans held less dissolved methane in stable form, encouraging further liberation. Increased heat also intensified chemical weathering of continental rocks, yet the rate of volcanic carbon input exceeded the capacity of these processes to restore balance quickly. The carbon cycle, once buffered by feedbacks that moderated change, now operated under strain, with inputs and responses drifting out of equilibrium. The atmosphere and ocean together functioned as a coupled system. As atmospheric carbon dioxide increased, more dissolved into surface waters, altering pH and influencing marine chemistry. Warmer surface layers reduced vertical mixing, further isolating deeper waters and affecting oxygen distribution. These shifts fed back into biological productivity, which in turn influenced carbon burial rates. Each component responded to the others, creating cycles of reinforcement that magnified initial perturbations. Over hundreds of thousands of years, this pattern of accumulation and feedback nudged the climate toward states rarely experienced in Earth's previous history. Ice-free poles, expanded arid belts, and warmer ocean basins became more common features of the planet's environmental mosaic. The greenhouse effect, once a stabilizing presence within moderate bounds, now operated at intensified levels. Yet even within this escalation, the system retained complexity. Chemical weathering continued drawing down carbon at a measured pace, and oceanic processes absorbed portions of atmospheric gases, though insufficiently to halt the trend immediately. Runaway warming in this context did not imply infinite escalation, but rather a period in which feedbacks amplified change faster than stabilizing mechanisms could respond. The atmosphere thickened with greenhouse gases, the oceans absorbed both heat and carbon, and the planet's thermal equilibrium shifted to a hotter baseline. Through these intertwined cycles, the groundwork was laid for further transformations that would reshape ecosystems across land and sea, carrying the late Permian world toward thresholds it had not previously crossed. Beneath the rising warmth of the atmosphere, the oceans absorbed more than heat. The surface waters, in constant exchange with the air above, drew in increasing amounts of carbon dioxide, dissolving it molecule by molecule into their vast expanse. When carbon dioxide enters seawater, it does not remain unchanged. It reacts with water to form carbonic acid, a compound that subtly alters the chemistry of the surrounding environment. This transformation unfolds invisibly, yet its consequences ripple through every layer of marine life. As carbonic acid forms, it releases hydrogen ions, lowering the pH of seawater. The shift is measured in small numerical increments, yet even slight declines represent significant chemical change within the ocean's buffering system. Marine organisms that rely on carbonate ions to build shells and skeletons find their construction materials less available. Calcium carbonate, the mineral foundation of many reefs and planktonic shells, becomes more difficult to precipitate as acidity increases. Structures that once formed with relative ease require greater biological effort, slowing growth and weakening resilience. In shallow tropical seas, where complex reef communities had flourished, this chemical alteration began to erode the scaffolding of ecosystems. Corals and other reef-building organisms depend on stable carbonate chemistry to maintain their frameworks. As saturation states decline, skeletal growth falters, and existing structures become more susceptible to dissolution. Reef habitats, already strained by temperature changes, now faced additional stress from shifting chemistry. The intricate architecture that supports diverse marine communities grew fragile. Microscopic plankton experienced similar challenges. Many species of foraminifera and other calcareous microorganisms construct delicate shells that play a vital role in marine food webs. When their ability to calcify diminishes, population dynamics shift. These microorganisms form the base of many oceanic chains, feeding small grazers, which in turn nourish larger predators. A reduction in calcifying plankton alters nutrient cycling and energy transfer through the water column. The effect is not confined to a single trophic level, but spreads outward through interconnected relationships. As acidification intensified, some organisms adapted temporarily by altering shell composition or reducing calcification rates, yet such adjustments carried energetic costs. Species less tolerant to chemical change declined, narrowing biodiversity within certain regions. The composition of marine communities began to shift toward organisms better suited to warmer, more acidic waters. In areas where oxygen was also decreasing, the combined stresses compounded, further limiting viable habitats. Evidence of this transition is etched into marine sediments worldwide. Layers corresponding to this interval display changes in carbonate content, with reductions in reef-derived limestone and alterations in microfossil assemblages. In some sequences, signs of carbonate dissolution appear directly within the rock record, indicating that ocean waters had crossed thresholds affecting mineral stability. The fossil distribution reflects both selective survival and ecological restructuring, revealing not a single instantaneous collapse, but a progression of biochemical stress. Ocean acidification therefore acted as a quiet yet pervasive force during this period of planetary upheaval. By altering the chemistry upon which countless organisms depended, it reshaped ecosystems from their foundations upward. The sea, long a stabilizing presence within Earth's climate system, became a conduit through which atmospheric change exerted deeper influence. Dissolved carbon-linked air and water in a shared transformation, one that reverberated through shell, skeleton, and sediment, marking another step in the unfolding reconfiguration of the late Permian world. In the deep basins far below the sunlit surface, a quiet suffocation began to unfold. The waters that once circulated steadily between surface and depth grew increasingly stratified, layered by temperature and density into more isolated tiers. As global temperatures rose, the ability of seawater to retain dissolved oxygen diminished. Warmer water simply holds less gas, and even slight increases in heat reduce its capacity to store the oxygen upon which marine life depends. What might appear negligible at the surface becomes profound when extended across the volume of entire oceans. Surface waters, heated and lightened, remained afloat above cooler, denser layers beneath. This separation weakened the vertical mixing that ordinarily refreshes deep basins with oxygen drawn from contact with the atmosphere. Currents that once carried oxygen-rich water downward slowed, interrupted by strengthened thermal gradients. The ocean's great conveyor systems, driven by contrasts in temperature and salinity, adjusted under the pressure of warming, altering pathways that had distributed life, sustaining gases across hemispheres. As ventilation declined, oxygen concentrations in certain regions dropped below thresholds required by many organisms. Localized pockets of hypoxia emerged first along continental margins and in restricted basins where circulation was already constrained. These areas gradually expanded as stratification intensified. Microbial communities adapted to low oxygen conditions gained dominance in some of these waters, metabolizing organic matter through pathways that did not rely on abundant oxygen. The chemistry of the seafloor began to shift in response. With continued warming and nutrient changes linked to earlier disruptions, productivity patterns also transformed. In some areas, blooms of plankton proliferated near the surface, later sinking as organic detritus to deeper waters. The decomposition of this material consumed additional oxygen, further lowering levels in already stressed zones. This biological drawdown interacted with reduced physical mixing, deepening the oxygen deficit. Anoxic zones, regions effectively devoid of dissolved oxygen, spread horizontally across the seafloor in expanding belts. In fully anoxic conditions, different chemical processes dominate. Iron and manganese cycles shift, and sulfur-reducing bacteria flourish, producing hydrogen sulfide as a metabolic byproduct, while complete euxinia, characterized by both anoxia and sulfide accumulation, may not have blanketed every ocean basin simultaneously. Evidence suggests that such states developed episodically and regionally. The presence of certain trace elements in sediment layers, including molybdenum and uranium anomalies, indicates prolonged intervals of oxygen-poor bottom waters. The geological record preserves these transitions with quiet precision. Black shale deposits, rich in organic carbon and formed under low oxygen conditions, appear widely across marine sections, dating to this interval. Their dark coloration reflects enhanced preservation of organic matter that would normally decay more completely in well-oxygenated settings. These shales often contain specific isotopic signatures and microfossil assemblages consistent with stressed ecosystems and altered circulation. As oxygen-deprived waters expanded, habitable marine space contracted. Species adapted to well-ventilated environments retreated or declined, replaced by organisms more tolerant of hypoxia. Reef ecosystems, already challenged by chemical shifts, found additional stress in diminished oxygen availability. The ocean, once a dynamic medium circulating nutrients and gases through interconnected basins, had begun to lose its breath. Its internal motions slowed, its chemical gradients sharpened, and its deep realms turned increasingly inhospitable. Through incremental changes in physics and biology, the sea entered a state unlike the balanced conditions that had prevailed before, marking another stage in the cascading transformation of the late Permian world. Where oxygen thinned to near absence, other forms of metabolism quietly advanced. In waters that had lost their breath, communities of sulfate-reducing bacteria expanded across seafloor sediments and within stagnant basins. These microorganisms thrive where oxygen no longer dominates chemical reactions, drawing energy instead from sulfur compounds dissolved in seawater. As organic matter settled from above and decomposed under anoxic conditions, these bacteria multiplied, converting sulfate into hydrogen sulfide as a metabolic byproduct. The transformation was invisible at first, a shift occurring molecule by molecule in darkened depths. Hydrogen sulfide is a gas, both soluble and volatile, capable of accumulating in stratified waters when production exceeds dispersal. In restricted basins and along continental margins where circulation remained weak, concentrations likely increased steadily. The gas binds readily with iron, forming dark minerals that imprint themselves within sediment layers. Yet, if iron supplies become saturated or depleted, dissolved sulfide can build within the water column itself. In such chemically layered oceans, a sharp boundary may have separated relatively oxygenated surface waters from deeper sulfide-rich zones. Episodes of mixing, whether driven by storm systems, changing currents, or thermal shifts, could have allowed portions of this sulfide-rich water to rise toward the surface. Even moderate exposure to hydrogen sulfide can be toxic to many marine organisms, interfering with cellular respiration by disrupting mitochondrial function. Fish and invertebrates encountering such conditions would experience rapid physiological stress. Reef communities already weakened by warming and acidification faced additional pressure from chemical toxicity. Species tolerant of low oxygen might survive briefly, yet sulfide concentrations beyond certain thresholds become lethal across broad taxonomic groups. The implications extended beyond marine habitats. If hydrogen sulfide reached the atmosphere in sufficient quantities, localized contamination could have occurred. In the lower atmosphere, sulfide oxidizes relatively quickly, yet sustained release might have influenced atmospheric chemistry, contributing to acid deposition and altering ultraviolet shielding under certain conditions. Some hypotheses propose that large-scale eosinic events, where anoxic and sulfide-rich waters dominate, could even have episodically injected sulfide into coastal air masses, affecting terrestrial ecosystems near shorelines. While direct atmospheric measurements are impossible for this interval, indirect evidence provides clues. Geological signatures consistent with expanded euxinia appear in sedimentary records from multiple regions. Black shales enriched in pyrite, a mineral formed when iron reacts with hydrogen sulfide, occur in layers corresponding to the extinction interval. Isotopic anomalies in sulfur compounds indicate shifts in global sulfur cycling, suggesting intensified microbial sulfate reduction. Biomarker molecules, derived from green sulfur bacteria, organisms that inhabit stratified, light penetrated yet sulfide rich waters, have been detected in some deposits, implying that hydrogen sulfide reached shallow photic zones in certain basins. Such evidence points toward episodes when toxic conditions were not confined to isolated pockets, but spread across broader swaths of the ocean. The interplay between oxygen depletion and sulfide production formed another reinforcing loop within the destabilizing system. As anoxia expanded, sulfate reduction increased. As sulfide accumulated, marine habitats contracted further. The sea, altered chemically and thermally, carried within it compounds inimical to much of its former life. Through microbial processes operating at microscopic scales, large-scale consequences emerged, shaping an environment where survival demanded tolerance to conditions rarely encountered before. Across the broad interior of the supercontinent, vegetation had once softened seasonal extremes, rooting soil in place and drawing carbon quietly from the air. As atmospheric and oceanic changes intensified, those terrestrial communities began to falter. Heat waves grew longer. Rainfall patterns shifted in uneven pulses, and prolonged droughts alternated with sudden, heavy downpours. Plants adapted to earlier conditions found themselves stressed beyond familiar limits. Leaf canopies thinned, growth slowed, and in some regions, entire forest belts retreated. The loss of plant life did not occur everywhere at once. It unfolded unevenly across latitudes and elevations, yet the trend appears in sedimentary records from widely separated basins. Charcoal layers suggest episodes of increased wildfire, likely fueled by heightened temperatures and drier intervals. Fires removed protective ground cover and exposed soil directly to wind and rain. Where roots once bound the surface, bare earth lay vulnerable to erosion. Without stabilizing vegetation, rainfall carved more aggressively into slopes and plains. Rivers carried greater loads of sediment toward lowland basins and coastal margins. Coarse materials settled first, followed by finer silts that clouded waterways and altered delta systems. Increased sedimentation reshaped channels and shallows, burying habitats that had supported diverse assemblages. In marine settings, this influx of terrestrial debris may have compounded chemical stresses already affecting shallow ecosystems. The decline of forests also influenced atmospheric chemistry through reduced carbon sequestration. Growing plants act as dynamic reservoirs of carbon, capturing carbon dioxide during photosynthesis and storing it in wood, leaves, and soils. When vegetation diminishes, both the uptake of carbon slows and stored organic matter becomes more vulnerable to decay and combustion. The balance between carbon input and removal shifts subtly but persistently. Decomposition of dying plant material releases additional carbon dioxide back into the atmosphere, reinforcing warming trends already underway. Soil systems, long nurtured under forest canopies, experienced transformation as well. Organic rich horizons eroded or oxidized, reducing fertility and further limiting regrowth. Nutrient cycles disrupted by vegetation loss altered the capacity of landscapes to recover quickly. In some areas, wetlands expanded temporarily under changing hydrological patterns, while in others, prolonged aridity prevented reestablishment of dense plant cover. The terrestrial biosphere entered a period of instability that mirrored changes unfolding in the oceans. Evidence for this transition appears vividly in microscopic fossils, pollen grains and spores, resilient structures produced by plants, accumulate in sediment layers and offer detailed records of botanical communities. In strata approaching the extinction boundary, shifts in pollen assemblages reveal declines in diverse forest taxa and increased representation of opportunistic species adapted to disturbed environments. In certain sequences, fungal spores become unusually abundant, possibly reflecting widespread decomposition of dead vegetation. Such patterns suggest intervals during which forests experienced extensive dieback. The collapse of terrestrial vegetation carried consequences that extended beyond individual ecosystems. Reduced plant cover altered albedo, affecting how much solar energy was absorbed or reflected at the surface. Changes in transpiration modified regional humidity and cloud formation, subtly influencing atmospheric circulation. As rivers delivered increased sediment to coastal margins, nutrient fluxes into nearshore waters shifted, linking land and sea in shared transformation. Through these interconnected processes, the retreat of forests became both a symptom and a driver of environmental change. Landscapes, once moderated by layered canopies and rooted soil, grew more exposed, more prone to fluctuation. Carbon that had cycled through trunks and leaves found new pathways through air and sediment. The terrestrial realm, like the oceans before it, entered a phase of contraction and reorganization, reflecting the deepening imbalance shaping the late Permian world. Air can grow warm enough to challenge life, yet it is the combination of heat and humidity that determines the true boundary of survival. Temperature alone does not define danger. The body relies on evaporation to shed excess warmth. When sweat or moisture on skin evaporates, it draws heat away, maintaining internal stability. This process depends on the surrounding air being able to accept additional water vapor. If the atmosphere already holds high moisture content, evaporation slows and cooling becomes less efficient. The measure that captures this balance is known as wet bulb temperature, a value reflecting how effectively evaporation can occur under given conditions. In simple terms, wet bulb temperature represents the lowest temperature air can reach through evaporative cooling. When this value approaches the temperature of the human body, or that of many warm-blooded animals, the margin for survival narrows. Sustained exposure to a wet bulb temperature near 35 degrees Celsius can overwhelm the capacity for heat dissipation, even in shade, even with airflow. Reptiles, though capable of regulating body temperature behaviorally, face similar physiological constraints when environmental heat persists without respite. During the late Permian warming, climate models and isotopic reconstructions suggest that certain equatorial and low-latitude regions may have approached these critical thresholds episodically. Increased greenhouse gas concentrations elevated baseline temperatures, while altered circulation patterns influenced humidity distribution. Coastal margins, shallow seas, and interior basins may have experienced intervals when both heat and moisture combined to create oppressive conditions. In such climates, large terrestrial animals would find activity constrained to narrow temporal windows, seeking refuge in burrows, water bodies, or higher elevations when possible. As temperatures climbed further, habitable zones contracted geographically. Regions once capable of supporting diverse vertebrate faunas became marginal, then inhospitable for extended periods. Thermal stress reduces reproductive success, disrupts metabolic efficiency, and increases vulnerability to disease. For ectothermic reptiles, extreme heat can impair enzymatic processes, while for early synapsids and other warm-blooded lineages, sustained high, wet bulb conditions challenge internal cooling mechanisms. Behavioral adaptations may provide temporary relief, yet persistent climate states, exceeding physiological tolerance, lead to population decline. The contraction of viable habitat did not occur uniformly across the globe. Higher latitudes may have retained more moderate conditions, offering temporary refugia. Elevation gradients created microclimates, allowing some species to persist in cooler uplands or along river corridors. Yet migration requires connected landscapes and sufficient resources. As forests retreated and hydrological patterns shifted, corridors narrowed. The biosphere faced not only chemical and ecological stress, but also shrinking physical space, in which temperature and humidity remained within survivable bounds. Thermal stress also influenced freshwater systems. Lakes and rivers warmed, reducing dissolved oxygen and compounding aquatic challenges. Amphibious species dependent on both land and water encountered compounded limits as both realms grew less forgiving. Heat waves layered upon background warming increased variability, pushing some regions intermittently beyond critical wet bulb thresholds before retreating slightly, then returning again. In this evolving climate, lethality was not confined to singular dramatic moments. It emerged from persistent exceedance of physiological limits across landscapes. The combination of elevated temperature and humidity defined new boundaries of endurance. Life adapted where it could, retreated where refuge existed, and vanished where conditions remained relentlessly beyond tolerance. Through the subtle mathematics of heat exchange and atmospheric moisture, the warming planet reshaped the map of survivable terrain, narrowing the zones within which complex terrestrial life could endure. High above the surface, invisible reactions were unfolding within the thickened air. Volcanic plumes carried not only carbon dioxide, but substantial quantities of sulfur dioxide, a gas that reacts readily with atmospheric moisture. Once aloft, sulfur dioxide oxidizes and combines with water vapor to form sulfuric acid droplets. These droplets gather within clouds and eventually fall as precipitation, altering the chemistry of rain itself. What descends appears no different from ordinary rainfall, yet its composition carries a sharper edge. Acid rain interacts first with leaves and exposed surfaces. On vegetation already weakened by heat and drought, repeated exposure to acidic precipitation can damage tissues, leach nutrients from foliage, and impair photosynthetic efficiency. Soils beneath forests experience parallel shifts. Hydrogen ions from acid rain displace essential minerals such as calcium and magnesium, carrying them downward through leaching. Nutrient balances shift gradually, reducing the capacity of plants to regenerate after disturbance. Root systems, already stressed by climatic extremes, must contend with altered soil chemistry that limits access to vital elements. As vegetation declines further, the stabilizing influence of plant cover diminishes. Acidified soils support fewer robust root networks, intensifying erosion during heavy rainfall events. The materials washed from land carry dissolved ions and fine sediments toward rivers and coastal zones. These inputs reshape aquatic chemistry, modifying nutrient ratios delivered to nearshore waters. Elevated fluxes of certain elements can stimulate localized blooms of microorganisms, which upon decomposition consume additional oxygen, linking terrestrial chemical shifts to marine stress. In the atmosphere itself, sulfur compounds influence radiative balance in complex ways. Sulfate aerosols reflect portions of incoming sunlight, producing short-lived cooling at regional scales. Yet, such cooling overlays a background of greenhouse warming, resulting in variable patterns of temperature and precipitation. Regions downwind of major eruptive centers may have experienced repeated cycles of acidic precipitation interspersed with transient dimming of sunlight. Vegetation subjected to these oscillations encountered both chemical injury and reduced light availability, further limiting growth. Ocean chemistry also responded to sulfur deposition. Although seawater possesses buffering capacity, sustained influxes of acidic compounds can contribute to localized pH fluctuations, particularly in restricted basins. Nutrient imbalances arising from altered weathering rates on land feed into coastal ecosystems, adjusting the productivity of plankton communities. Shifts in plankton composition reverberate upward through food webs and influence carbon cycling dynamics, already strained by volcanic inputs. Geological records preserve indirect traces of these atmospheric reactions. Sulfur isotopic signatures in sedimentary sulfates and evaporites reflect perturbations in the sulfur cycle during this interval. Increased deposition of certain sulfate minerals suggests intensified weathering and transport processes consistent with enhanced acidic precipitation. Clay mineral assemblages in terrestrial deposits reveal chemical alteration linked to low pH conditions, while patterns of plant decline in fossil pollen records align temporally with episodes of heightened volcanism and atmospheric sulfur loading. Through these interconnected pathways, acid rain became more than a chemical curiosity. It acted as a multiplier of stress, compounding the effects of warming, oxygen depletion, and ecosystem contraction. Atmospheric chemistry and surface processes intertwined, ensuring that disturbances aloft translated into tangible consequences on land and sea. The sky itself participated in reshaping the biosphere, carrying volcanic byproducts across continents and releasing them gradually into soils and waters. In this manner, atmospheric sulfur joined carbon and heat as part of a broader cascade, reinforcing the instability that was unfolding across the late Permian world. Deep beneath continental shelves, within sediments compacted by time and pressure, methane lay trapped in crystalline cages of ice, known as hydrates. These structures form where low temperatures and sufficient pressure allow water molecules to encase methane gas in a lattice that remains stable so long as conditions do not change. For long intervals, such deposits remain locked below the seafloor, sequestering vast amounts of carbon in solid form. They are sensitive reservoirs, balanced delicately between temperature and pressure. As ocean waters warmed from sustained greenhouse forcing, the stability zone for methane hydrates shifted upward through the sediment column. Even modest increases in bottom water temperature can destabilize hydrate layers resting near their threshold. When destabilization occurs, methane escapes from its frozen cages, migrating upward through sediments and into the ocean. In some cases, Gas seeps diffuse gradually, dissolving in seawater and oxidizing into carbon dioxide. In others, more vigorous releases may vent into the water column in bursts. Methane possesses a greenhouse potential significantly greater than carbon dioxide over shorter timescales. Molecule for molecule, it absorbs infrared radiation more efficiently, enhancing the retention of heat within the atmosphere. If sufficient quantities reach the air before oxidizing, methane can amplify existing warming rapidly. During the late Permian interval, geochemical evidence suggests episodes when additional carbon entered the atmosphere in forms consistent with methane release. The effect would not have replaced volcanic carbon input, but rather intensified its influence. Rapid warming spikes inferred from sedimentary records align with phases of isotopic change. Carbon isotopes, preserved in marine carbonates and organic matter, show abrupt negative excursions, shifts toward lighter carbon that indicate the addition of isotopically light carbon into the system. Methane derived from biological or thermogenic sources carries this lighter signature. While volcanic emissions contribute carbon as well, the magnitude and pattern of certain isotopic shifts imply supplemental input beyond mantle sources alone. Once released, methane initiates feedback cycles. Rising temperatures destabilize additional hydrates, releasing more methane and reinforcing warming. At the same time, oxidation of methane in the ocean consumes oxygen, linking hydrate destabilization to further deoxygenation. Increased atmospheric methane also influences tropospheric chemistry, affecting concentrations of other gases and potentially altering cloud formation patterns. The climate system, already strained by volcanic forcing and disrupted carbon cycling, absorbs this new pulse as an added acceleration. The destabilization of hydrates does not occur uniformly across all basins. Regions with thick sediment accumulations and steep thermal gradients are particularly vulnerable. Continental shelf margins, warmed by circulating currents altered in previous stages, may have served as focal points for methane release. Evidence of disturbance appears in sedimentary structures associated with fluid escape, such as breccias and disrupted bedding, though not all such features can be uniquely attributed to methane. Still, combined with isotopic data and timing correlations, a compelling narrative of hydrate involvement emerges. Through this process, carbon long stored in frozen matrices return to active circulation. The transition from stable hydrate to free methane illustrates how climate thresholds can unlock reservoirs previously insulated from surface change. Each additional increment of greenhouse gas narrowed the planet's margin for equilibrium. Methane's contribution, layered atop volcanic emissions and weakened carbon sinks, represents another strand in the tightly woven network of feedbacks reshaping the late Permian world, drawing it further into a state of amplified warmth and ecological vulnerability. In the layered archives of stone, a boundary appears where abundance yields abruptly to absence. Fossil-rich strata filled with shells, bones, and intricate reef frameworks give way to thinner horizons marked by scarcity. This transition, preserved across continents and ocean basins, defines what is now known as the Great Dying, the most severe mass extinction recorded in Earth's history. It was not a single moment, but a pulse that unfolded over tens of thousands of years, perhaps longer in some regions, yet in geological terms, it remains startlingly swift. Marine ecosystems suffered losses of staggering magnitude. Between 90 and 96% of marine species disappeared from the record. Entire clades that had flourished for millions of years vanished or dwindled to a handful of survivors. Reef systems, once complex architectures of living limestone, collapsed almost entirely. The intricate communities of corals, sponges, brachiopods, and other reef builders failed to reestablish their former networks, leaving long intervals in which reef structures are rare or absent in the stratigraphic sequence. Ocean basins that had supported diverse assemblages of ammonoids, trilobites, and crinoids became comparatively sparse. On land, the toll was scarcely less profound. Approximately 70% of terrestrial vertebrate species are estimated to have been lost. Synapsids that had dominated Permian landscapes declined sharply, along with numerous amphibian and reptilian lineages. The contraction of habitable zones under sustained heat and chemical stress left many regions incapable of supporting large, complex animals. Insect communities, often resilient across environmental change, also experienced notable extinctions during this interval, as evidenced by reductions in certain fossilized wing and body forms. Such a decline among insects underscores the breadth of ecological disruption. The extinction pulse appears to have occurred in phases rather than as a single catastrophic event. Stratigraphic sections from different parts of the world reveal intervals of intensified loss, punctuated by brief periods of relative stability. These pulses correspond in timing with geochemical indicators of environmental stress, including shifts in carbon isotopes, expanded anoxia, and volcanic activity. The cumulative effect of repeated stressors narrowed survival options for species already strained by warming, acidification, and oxygen depletion. In marine sediments, the decline in biodiversity is visible as a simplification of fossil assemblages. Diverse communities give way to a few opportunistic species capable of tolerating harsh conditions. Black shales and other indicators of low oxygen environments often coincide with these impoverished faunas. On land, vertebrate fossil records show abrupt turnovers, with once common taxa replaced by smaller or more adaptable forms. The biosphere did not empty entirely, yet it was reduced to a shadow of its former complexity. Recovery would prove slow. After the extinction peak, ecological systems remained simplified for extended periods, sometimes for millions of years. Reef ecosystems, in particular, required prolonged intervals before rebuilding structures comparable to their earlier forms. The Great Dying, therefore, represents not only an event of immense loss but also a protracted reconfiguration of life's architecture. In its wake, evolutionary pathways opened for new lineages to diversify, yet the silence in the fossil record at the boundary itself testifies to a collapse unlike any other in Earth's known history. After the sharp boundary of extinction, the rock record grows quiet in a different way. Layers that follow contain fewer shells, fewer bones, fewer traces of the intricate communities that once filled seas and landscapes. The planet did not fall silent, yet its biological chorus softened to a handful of persistent notes. Ecosystems that had once been layered webs of interaction simplified into fragile assemblies of survivors, each enduring within narrowed limits. In marine environments, diversity contracted to small clusters of taxa capable of tolerating warm, oxygen-poor, and chemically unstable waters. Opportunistic bivalves, certain gastropods, and a few resilient ammonoid lineages appear repeatedly in early Triassic sediments, often dominating assemblages that previously would have hosted dozens of coexisting forms. Reef frameworks, once architectural strongholds of biodiversity, are largely absent for extended intervals. Instead of towering carbonate structures, sediments show microbial mats and low complexity buildups, suggesting communities reorganized around organisms able to thrive under reduced competition and altered chemistry. On land, the pattern echoes the sea. fossil records from terrestrial basins reveal a striking reduction in vertebrate diversity. A small number of hardy synapsid and reptilian groups persist, occupying ecological roles once divided among many specialized lineages. The dominance of such survivors suggests that resilience depended less on complexity and more on flexibility, broad diets, and tolerance to heat and scarcity. Plant communities, too, appear simplified in some regions, with pioneer species and hardy seed plants spreading across landscapes disturbed by climate and soil instability. The pace of recovery lagged far behind the duration of the extinction pulse itself. Even after major environmental stressors began to ease, ecosystems required time to rebuild structural and functional complexity. Nutrient cycles, predator-prey relationships, and habitat networks must reassemble from limited genetic and ecological foundations. The fossil record of the early Triassic often reflects this delay, with extended intervals characterized by low diversity and limited morphological innovation. Such prolonged simplification distinguishes this event from other mass extinctions where recovery unfolded more rapidly. Sedimentary sequences from this period frequently contain thin fossil assemblages interspersed with layers rich in indicators of environmental stress, including evidence of continued warming and episodic anoxia. The scarcity of fossils in some strata may reflect both genuine biological reduction and conditions unfavorable to preservation. Yet, across multiple continents and marine basins, the pattern of diminished diversity is consistent, indicating that the biosphere operated at reduced capacity. This near emptiness did not imply the absence of evolutionary potential. Rather, it represents a reset in ecological architecture. With numerous niches vacated, surviving lineages carried forward opportunities for diversification once conditions stabilized. The biosphere, stripped of much of its former complexity, functioned in a simplified state that would gradually seed new radiations. In this interval, Earth approached a biological threshold not previously recorded in its history. The network of life, though not entirely broken, was pared down to essential strands. The nearly empty planet persisted in this attenuated state for extended spans of time, its landscapes and seas inhabited by fewer species interacting within narrower bounds. From this simplified foundation, the next chapter of evolutionary innovation would eventually emerge. But, for a time, the world bore the imprint of profound loss, its living systems reduced, yet not extinguished. Long after the extinction pulse had narrowed the web of life, another quiet variable lingered in question: the composition of the air itself. Oxygen, so fundamental to complex metabolism, has not remained constant through Earth's history. Its concentration rises and falls over millions of years, shaped by burial of organic carbon, volcanic degassing, and the slow chemistry of weathering. During the late Permian and earliest Triassic, evidence suggests that this vital gas may have declined to levels far lower than those familiar today. Clues to atmospheric oxygen are preserved indirectly in minerals and isotopic signatures rather than in trapped samples of ancient air. Certain sedimentary rocks contain redox-sensitive elements whose behavior depends on oxygen availability. The distribution of iron formations, the presence of specific sulfur isotope patterns, and the chemistry of paleosols all provide fragments of information. Charcoal abundance in sedimentary layers also offers insight, since widespread wildfires require minimum oxygen thresholds to sustain combustion. Variations in charcoal records across the boundary interval hint that atmospheric oxygen concentrations may have dipped significantly. Models integrating these geochemical proxies suggest that oxygen levels might have fallen below 15% during parts of the early Triassic, compared to about 21% in the present atmosphere. For large animals with high metabolic demands, such a reduction has meaningful physiological consequences. Lower oxygen partial pressure reduces the efficiency of diffusion into the bloodstream and limits aerobic performance. Endurance declines, reproductive success may falter, and vulnerability to thermal stress increases, especially in already warm climates. Reptiles and early synapsids possessed varied respiratory strategies, yet all relied on sufficient oxygen gradients to sustain cellular respiration. In combination with elevated temperatures, reduced oxygen amplifies physiological strain. Heat accelerates metabolic processes, increasing oxygen demand, while diminished atmospheric supply restricts intake. The overlap of warming and hypoxia narrows the range of conditions in which complex vertebrates can thrive. Smaller body sizes, observed in some early Triassic faunas, may reflect selective pressures favoring organisms with lower overall oxygen requirements. Geochemical reconstructions do not imply a complete collapse of atmospheric oxygen to unbreathable levels. Photosynthetic organisms, particularly marine phytoplankton and terrestrial plants that survived, continued to produce oxygen while weathering and burial processes removed reduced carbon. Yet the balance appears to have shifted enough to approach critical thresholds for many species. The margin between survivable and stressful conditions may have been thinner than at most other times in the Phanerozoic. When considered alongside warming, ocean anoxia, and toxic episodes, reduced atmospheric oxygen represents another layer of constraint tightening around the biosphere. Earth did not lose its oxygen entirely, yet it may have hovered near levels that constrained biological complexity. The fossil record simplified communities and reduced body sizes align with such a scenario, though disentangling cause and effect remains challenging. The question of how close oxygen fell to truly critical lows remains an active area of research. What emerges from available evidence is a portrait of a planet operating near multiple thresholds simultaneously. Oxygen levels likely fluctuated rather than dropping in a single, abrupt step, influenced by feedbacks among climate, carbon burial, and volcanic input. Within this shifting atmosphere, survivors endured conditions that tested physiological limits. The air itself, once taken for granted as a stable medium, became another variable in the delicate equation that determined whether Earth's biosphere could persist beyond the brink. Far beneath the fractured crust and convecting mantle, motion continued in silence. The outer core, composed largely of liquid iron alloy, churned under immense pressure and heat, generating a magnetic field that extended outward into space. This geodynamo did not falter during the climatic and biological crises unfolding at the surface. While oceans stagnated and forests withered, the invisible shield produced deep within the planet persisted, shaping interactions between Earth and the Sun. A magnetic field does not regulate climate directly, yet it influences the long-term stability of a planet's atmosphere. Charged particles streaming outward from the Sun, collectively known as the solar wind, constantly flow past planetary bodies. When such particles encounter a strong magnetic field, they are deflected or guided along field lines, often toward the poles where auroras glow. Without this magnetic deflection, solar wind can interact more directly with upper atmospheric layers, imparting energy that accelerates the loss of lighter molecules into space. Earth's gravity provides the primary anchor for atmospheric gases, yet magnetic shielding reduces the rate at which energetic particles erode that gaseous envelope over geological time. By maintaining its dynamo, Earth preserved a buffer against gradual atmospheric stripping. Even amid elevated greenhouse gases and altered chemistry, the total mass of the atmosphere remained sufficient to sustain surface pressure compatible with liquid water. The contrast with Mars illustrates this distinction clearly. Geological evidence suggests that Mars once possessed a magnetic field generated by an active core. Magnetic signatures, preserved in ancient crustal rocks, indicate that its dynamo operated early in planetary history. Over time, as the smaller planet cooled and internal convection diminished, this magnetic field weakened and ultimately ceased. Without global magnetic protection, the Martian atmosphere became increasingly vulnerable to solar wind erosion. Measurements from orbiting spacecraft reveal ongoing atmospheric loss, driven by interactions with charged particles. Mars also lacks the mass of Earth, making gravitational retention of atmospheric gases less effective. Combined with the absence of a sustained dynamo, this lower gravity contributed to the thinning of its atmosphere over billions of years. Water that once flowed across its surface gradually disappeared, some lost to space, some trapped as ice. The transition occurred slowly in comparison to the rapid environmental upheaval of the late Permian on Earth. Yet the outcome demonstrates how atmospheric stability can erode without internal magnetic support. During the Permian crisis, Earth experienced extreme warming, oceanic anoxia, and major carbon cycle perturbations, yet its magnetic field endured. This persistence ensured that external space weather did not compound internal instability by accelerating atmospheric escape. Solar radiation continued to interact with the upper atmosphere, but within a protective framework that limited large-scale stripping. The balance between incoming solar particles and atmospheric retention remained intact, even as chemical composition shifted. Magnetic stability thus represents a deeper layer of planetary resilience. While surface systems approached biological thresholds, the geodynamo maintained continuity in Earth's interaction with its star. The forces reshaping climate and ecosystems operated primarily within the bounds of a stable atmospheric mass. The retention of this shield did not prevent environmental catastrophe, yet it preserved conditions necessary for long-term recovery. In the midst of profound upheaval at the surface, the planet's core continued its steady motion, sustaining a field that quietly safeguarded the envelope of air upon which life depends. Mass exerts a quiet authority over worlds. It determines how tightly a planet can hold the gases that gather above its surface, how firmly it can resist the steady tug of thermal motion and solar radiation. Earth's greater mass, more than 9 times that of Mars, grants it stronger gravity, and with that gravity comes a deeper atmospheric well. Molecules heated by sunlight move rapidly, yet fewer achieve the velocities required to escape entirely from Earth's pull. Over immense spans of time, this difference alters destiny. Planetary mass influences more than surface gravity alone. A larger planet retains internal heat for longer periods, sustaining tectonic and volcanic activity that replenishes atmospheric constituents. Even during intervals of upheaval, when volcanic gases contributed to warming and instability, the broader cycle of outgassing served as a mechanism for atmospheric maintenance. Carbon dioxide, water vapor, nitrogen, and other gases released from the mantle through volcanic processes replace losses that would otherwise thin the envelope of air. Without such renewal, gradual escape to space would reduce atmospheric pressure across geological eras. Mars, smaller and cooling more quickly, experienced a different trajectory. Its diminished gravity allows lighter gases to escape more readily, especially under the influence of solar wind and ultraviolet radiation. As internal heat waned and tectonic activity faded, volcanic outgassing decreased, reducing replenishment of atmospheric components. Over billions of years, this imbalance between loss and supply led to progressive thinning. What remains today is a tenuous atmosphere incapable of sustaining stable surface liquid water. On Earth, even amid late Permian crisis, the total mass of the atmosphere did not collapse. Greenhouse gases increased in concentration, altering composition and climate, yet overall pressure remained sufficient to support liquid oceans. Water vapor, a critical greenhouse component and integral part of the hydrological cycle, continued to circulate between sea, air, and land. Evaporation from warm oceans fed cloud systems, while condensation returned moisture as precipitation. Although patterns shifted and extremes intensified, the fundamental presence of abundant surface water anchored atmospheric dynamics. The retention of water vapor depends on both gravity and temperature. Excessive heating can drive water molecules to altitudes where photodissociation and escape become more efficient. In runaway greenhouse scenarios hypothesized for other planets, this process accelerates, potentially stripping oceans over time. During the Permian event, warming was substantial, yet it did not cross into the sustained extremes required for wholesale ocean loss. Earth's gravity limited rapid escape, while feedback mechanisms and eventual carbon drawdown prevented indefinite temperature escalation. Long-term volcanic outgassing also contributed to sustaining atmospheric mass through cycles extending beyond the extinction interval itself. While episodic eruptions introduced destabilizing pulses of carbon and sulfur, continuous mantle degassing over millions of years ensures that atmospheric inventories are not left solely to depletion pathways. Combined with a magnetic field that reduced erosion by solar wind, Earth maintained an envelope thick enough to preserve pressure and protect water in liquid form. Thus, the same forces that triggered climatic crisis did not unravel atmospheric retention entirely. Mass, gravity, internal heat, and ongoing outgassing formed a structural resilience beneath surface volatility. Earth's atmosphere transformed chemically and thermally, yet it remained bound to the planet, dense enough to moderate pressure and sustain oceans. The contrast with Mars highlights how differences in planetary scale and interior longevity shape whether atmospheric thinning becomes gradual loss or temporary perturbation. In Earth's case, the envelope endured, altered but not abandoned. Beneath continents and ocean basins, the surface of Earth is not fixed but divided into moving plates, thin relative to the planet's radius, yet powerful in their collective motion. Over millions of years, these plates drift, collide, sink, and renew. Mountains rise where boundaries converge, while new crust forms along spreading ridges. This ceaseless reshaping does more than sculpt landscapes. It underpins the long-term regulation of climate through the slow circulation of carbon between interior and surface. When rain falls upon exposed rock, it carries dissolved carbon dioxide absorbed from the atmosphere. This slightly acidic water reacts with silicate minerals, breaking them down chemically in a process known as weathering. The products of this reaction are transported by rivers to the oceans, where they contribute to the formation of carbonate sediments. In this way, atmospheric carbon becomes locked within marine sediments and eventually lithified into rock. Without tectonic motion, such burial would represent a one-way transfer. On Earth, however, oceanic crust bearing carbonate sediments is drawn downward at subduction zones, carrying carbon back into the mantle. This recycling is slow, unfolding over tens of millions of years, yet it provides a stabilizing feedback that moderates atmospheric composition. When volcanic activity increases carbon dioxide concentrations and global temperatures rise, chemical weathering accelerates. Warmer conditions enhance reaction rates and intensify precipitation in some regions, increasing the drawdown of carbon from the air. Conversely, during cooler intervals, weathering slows, allowing volcanic emissions to gradually rebuild atmospheric greenhouse levels. Through this interplay, plate tectonics supports a thermostat operating on geological timescales. During the crisis interval, volcanic outgassing overwhelmed this feedback temporarily, yet the underlying tectonic cycle persisted. Carbon continued to be buried within sediments and transported into the mantle, ensuring that excess greenhouse gases would not remain indefinitely. Even amid upheaval, the machinery of subduction and ridge spreading sustained the potential for long-term recovery. Without such processes, carbon introduced into the atmosphere might accumulate without an effective removal pathway, pushing climate toward more extreme and prolonged states. Mars presents a contrasting case. Geological observations suggest that while early Mars experienced volcanic activity, it lacks the ongoing global plate tectonic system characteristic of Earth. Its crust appears largely stagnant, without widespread subduction zones or continuous recycling of surface material into the mantle. In the absence of active plate tectonics, the carbon cycle operates differently. Weathering can remove atmospheric carbon dioxide, yet without efficient recycling, long-term stabilization is constrained. Coupled with diminished internal heat and reduced volcanic replenishment, the Martian system evolved along a more static trajectory. Earth's tectonic vigor stems from retained internal heat and a combination of planetary mass and composition that allow lithospheric plates to fracture and move. This mobility not only shapes continents but also sustains the chemical gradients driving carbon exchange. Over time, it moderates extremes and restores balance after perturbations. Through plate tectonics, the planet retains a mechanism for renewal. Carbon buried in ancient seas reemerges through magmatic arcs, new crust forms, and old crust sinks. Weathering responds to warmth, and subduction completes the cycle. Even when surface conditions strain the biosphere, this deep circulation continues. The role of plate tectonics in Earth's survival is not dramatic in the moment, yet across epochs it provides the quiet resilience that distinguishes a world capable of recovery from one locked in irreversible decline. There was no sudden silence in the volcanic provinces, no single day when eruptions ceased and calm returned. Instead, over spans far longer than human history can easily imagine, the intensity of outgassing began to ebb. The vast fissures that had once poured molten rock across northern latitudes grew less active. Pulses of lava became less frequent, their intervals stretching wider, their cumulative contribution to atmospheric carbon gradually diminishing. The planet did not cool at once. It merely stopped accelerating toward greater heat. As volcanic output declined, the processes that remove carbon from the atmosphere continued their quiet work. Rain fell upon exposed rocks across continents already reshaped by climatic extremes. Carbon dioxide dissolved into water formed weak carbonic acid, which reacted with silicate minerals at the surface. These reactions transformed feldspars and other silicates into clay minerals, while producing dissolved bicarbonate ions carried by rivers toward the sea. With each chemical exchange, a small portion of atmospheric carbon became tied to minerals and sediment, beginning its journey into long-term storage. Silicate weathering operates slowly, yet it responds to climate conditions. Higher temperatures and increased rainfall enhance reaction rates, accelerating the drawdown of carbon dioxide when greenhouse levels rise. As warmth persisted in the aftermath of peak volcanism, weathering rates likely remained elevated, particularly in newly exposed basaltic provinces where fresh rock offered abundant reactive surfaces. Basalt, rich in calcium and magnesium silicates, weathers relatively rapidly compared to older, more resistant crust. In this way, the very eruptions that contributed to warming also supplied material that would aid eventual stabilization. Rivers transported weathering products to ocean basins, where they participated in carbonate formation. Over time, these carbon-bearing compounds settled into sediments, adding to layers that could one day be drawn downward through subduction. The balance between atmospheric input and removal shifted subtly. With reduced volcanic emissions and sustained chemical weathering, atmospheric carbon dioxide began a slow descent. Cooling followed, not as a dramatic reversal but as a gradual adjustment of radiative equilibrium. Ocean circulation patterns, previously weakened by extreme warming, would have responded incrementally as temperature gradients changed. Cooler surface waters increase oxygen solubility and reduce thermal stratification, supporting renewed vertical mixing over extended intervals. The biosphere, though simplified, interacted with this shifting climate through photosynthesis and organic carbon burial, contributing modestly to carbon sequestration. Each feedback loop moved within a narrower range as greenhouse forcing lessened. The cooling unfolded over millions of years. Ice did not immediately return to polar regions, nor did ecosystems regain lost diversity overnight. The slow turning point is visible only in the broad arc of stratigraphy, where geochemical proxies indicate declining carbon isotope anomalies and gradual shifts toward less extreme conditions. Temperatures moderated, allowing habitable zones to expand beyond the compressed belts of the hottest phase. In this transition, Earth demonstrates the power of time coupled with feedback. No singular intervention restored balance. Instead, interacting processes accumulated their influence patiently. Volcanism quieted, weathering persisted, sediments stored carbon, and radiative forcing eased. The trajectory bent slowly away from runaway warmth toward a cooler baseline capable of sustaining renewal. The turning point was not an event but a long convergence of forces, marking the beginning of recovery within a world that had come perilously close to enduring change without return. At first, the change was almost imperceptible, not in the sky but in the quiet chemistry of water. In basins that had lingered in stagnation, traces of oxygen began to appear more consistently within the upper layers. Cooling at the surface increased the solubility of gases, allowing slightly greater amounts of dissolved oxygen to persist. Winds and temperature gradients, gradually re-establishing contrasts between regions, encouraged the slow renewal of vertical mixing. What had once been sharply stratified waters started to exchange their layers more frequently, though not yet with the vigor of earlier eras. Oxygenation is not a single event, but a process shaped by physics and biology alike. As surface waters cooled and circulation strengthened modestly, oxygen diffused downward in incremental steps. In parallel, photosynthetic organisms continued their work within sunlit zones. Even during the most reduced state of marine ecosystems, microbial communities capable of oxygenic photosynthesis endured. As environmental conditions stabilized, these microorganisms expanded, contributing to the gradual replenishment of oxygen within surface layers. The interplay between physical mixing and biological production slowly widened habitable space. Deep waters did not transform overnight. Anoxic and sulfidic pockets likely persisted regionally for extended intervals, particularly in restricted basins where circulation lagged. Yet, the widespread dominance of oxygen-free conditions appears to have receded over time. Sedimentary records from early Triassic sequences reveal shifts in trace elements that indicate improving redox conditions in certain marine settings. Black shales become less ubiquitous, and carbonate deposition reappears more consistently, suggesting renewed stability in water chemistry. In the absence of complex reef systems, microbial mats and simple carbonate structures initially defined much of the rebuilding process. Stromatolitic formations and other microbial-dominated buildups appear in some regions, occupying ecological space vacated by extinct reef builders. These communities demonstrate how life reorganizes from its most fundamental levels upward. Bacteria and algae form cohesive layers that trap sediment, stabilize substrates, and create new microhabitats. Though less architecturally elaborate than Permian reefs, they represent the first frameworks of renewed ecological structure. As oxygen levels improved and chemical conditions moderated, more complex organisms began to reoccupy marine niches. Surviving lineages of mollusks and other invertebrates diversified gradually, exploiting reduced competition. Food webs, once truncated, extended downward and upward again. Plankton communities became more varied, supporting larger predators in a cautious progression. This rebuilding was uneven across latitudes and basins, yet the overall trajectory bent toward increasing complexity. Ocean circulation, though altered from its Permian configuration, regained enough coherence to sustain broader exchange between surface and depth. Currents redistributed heat and nutrients more effectively, tempering extremes that had dominated the crisis interval. As mixing intensified, the link between atmosphere and deep ocean strengthened, reinforcing oxygenation feedbacks. The sea, which had once seemed to lose its breath, began drawing it again with steadier rhythm. Recovery did not erase memory. Geochemical signals and simplified faunas persisted for long spans, marking a world still in transition. Yet within this gradual stabilization lay the foundation for renewed evolutionary experimentation. Oxygenation processes, re-established circulation, microbial groundwork, and the patient assembly of food webs all contributed to a cautious resurgence. The oceans did not return to their previous state, but they crossed back over critical thresholds, re-entering conditions capable of sustaining expanding diversity. Through incremental adjustments in chemistry and motion, the marine realm moved from suppression toward regeneration, step by measured step. From the thinned tapestry of life, new threads began to appear, subtle at first, against a landscape still marked by loss. In the earliest Triassic, the survivors were not the dominant architects of the previous age, but species capable of enduring instability. They were generalists, opportunists, organisms with flexible diets and physiological tolerance broad enough to navigate fluctuating temperatures and oxygen levels. Their persistence formed the foundation upon which future ecosystems would rise. On land, certain synapsids weathered the extinction and diversified cautiously within the emptied niches. Among them were small, resilient forms whose metabolic strategies allowed survival in challenging climates. Alongside these survivors, early archosauromorph reptiles began to expand. These lineages, initially modest in number, carried anatomical innovations in limb posture and respiratory efficiency that would later prove advantageous. Their ascent did not occur in dramatic bursts, but through gradual occupation of ecological space vacated by extinct competitors. The absence of previously dominant groups reshaped evolutionary pathways. With fewer established predators and herbivores, evolutionary experimentation accelerated within surviving clades. Body plans diversified, sizes fluctuated, and new feeding strategies emerged. The early Triassic fauna may appear simplified when compared to pre extinction communities, yet within that simplicity lay potential energy for diversification. Each generation carried forward genetic variation shaped by extreme selection pressures of the preceding crisis. In the oceans, recovery followed a similarly uneven course. Microbial communities had stabilized foundational processes, preparing substrates for more complex organisms. Mollusks and certain echinoderms expanded gradually, reclaiming portions of marine habitats. Ammonoids, despite suffering significant losses, rebounded comparatively quickly, radiating into new forms and re-establishing roles as active predators. Fish lineages diversified as well, adjusting to altered food webs shaped by evolving plankton communities. Reef ecosystems remained sparse for extended intervals, yet patchwork buildups began to appear in some basins. Though less elaborate than their Permian predecessors, these new reefs signaled the reemergence of ecological engineering. As carbonate chemistry stabilized and oxygen levels improved in certain regions, calcifying organisms slowly rebuilt structural habitats. The process required time measured not in thousands, but millions of years, reflecting the depth of disruption that preceded it. The long-term evolutionary consequences of the extinction ripple through subsequent eras. The decline of earlier dominant synapsids opened pathways that eventually favored the radiation of dinosaurs in the Mesozoic. Marine ecosystems reorganized around new assemblages of predators and prey, altering nutrient cycling and energy transfer for millions of years. Patterns of biodiversity, body size distribution, and ecological specialization bear the imprint of this resetting event. Evolution after the Great Dying did not simply restore what had been lost. It redirected life along new trajectories shaped by altered climates and reorganized geographies. Survivors carried traits molded by heat, hypoxia, and chemical stress, influencing the direction of future adaptation. Over time, diversity expanded once more, yet it did so upon a foundation profoundly different from that of the late Permian world. In this gradual resurgence, the resilience of life becomes evident not through dramatic reversal, but through sustained persistence. From sparse beginnings, ecosystems assembled layer by layer, species by species. The biosphere, nearly emptied, found within its survivors the capacity to innovate again. Through patience measured in deep time, Earth's living systems regained complexity, not as replicas of the past, but as newly configured expressions of evolutionary possibility. Long after the ash settled and ecosystems began their slow reconstruction, a quieter inquiry remains embedded in the science of climate physics. How near did the planet move toward a state from which recovery would not have been possible? Geological records reveal extreme warming, profound ocean chemistry shifts, and widespread biological collapse, yet the Earth did not tip into irreversible planetary sterilization. The boundary between temporary crisis and permanent transformation is defined not only by fossils and sediments, but by the physics of atmospheric energy balance. Climate models built from radiative transfer equations and paleoclimate data allow researchers to explore theoretical thresholds. A runaway greenhouse scenario occurs when warming triggers feedbacks strong enough that outgoing infrared radiation no longer increases with temperature. Under such conditions, additional heat cannot escape efficiently into space, and surface temperatures rise rapidly until oceans evaporate extensively. Water vapor itself is a powerful greenhouse gas, amplifying heating and accelerating loss of liquid reservoirs. In extreme forms, this pathway resembles what is believed to have occurred on Venus. Venus offers a cautionary contrast. Its dense carbon dioxide atmosphere and proximity to the sun create surface temperatures high enough to melt lead. Evidence suggests that Venus may once have possessed more moderate conditions, yet without stabilizing feedbacks comparable to Earth's silicate weathering cycle and with higher solar insolation. It crossed a threshold into sustained runaway warming. Water vapor in its upper atmosphere underwent photodissociation, allowing hydrogen to escape to space. Over time, the planet lost most of its water, leaving behind a thick greenhouse envelope and a desiccated surface. During the late Permian event, Earth approached significant warming, perhaps increasing global temperatures by several degrees beyond previous baselines. However, modeling studies indicate that the combination of solar input, atmospheric composition, and planetary parameters did not exceed the radiation limit required for a true runaway greenhouse. Outgoing long-wave radiation continued to rise with surface temperature, permitting some stabilization even amid strong greenhouse forcing. The oceans, though stressed and partially anoxic, did not evaporate wholesale. The thresholds not crossed are as instructive as those that were. Earth retained sufficient cloud cover dynamics, reflective feedbacks, and carbon removal mechanisms to prevent unbounded warming. Silicate weathering, even if temporarily overwhelmed, persisted as a long-term moderating influence. The planet's distance from the sun maintained solar input below the level necessary to trigger irreversible water vapor feedback at a global scale. These physical margins provided a buffer, narrow yet consequential. Assessing the margin of planetary safety involves integrating geological evidence with climate physics. Isotopic excursions and sedimentary indicators reveal intense perturbation, yet they also suggest that atmospheric carbon dioxide concentrations, though elevated, remained below levels predicted to induce complete ocean evaporation. The crisis illustrates how multiple feedbacks can amplify warming dramatically without breaching absolute physical limits. The difference between severe greenhouse conditions and irreversible runaway lies in energy balance and feedback strength. Earth during the Permian event appears to have hovered near significant thresholds without crossing the final boundary. The margin was not vast. It was a matter of interacting variables, remaining within constrained ranges. That constrained resilience allowed temperatures eventually to decline and oceans to persist. In examining how close was too close, the narrative shifts from biology to planetary physics. The extinction reshaped life profoundly, yet the underlying energy framework of the planet remained within reversible bounds. Earth endured near its climatic limits, but not beyond the point where radiative equilibrium could reassert control. Through that narrow margin, recovery remained possible, and the biosphere found space, however fragile, in which to begin again. Across the inner solar system, two neighboring planets reveal sharply different outcomes written over deep time. One world thinned slowly, its atmosphere leaking away across billions of years, until rivers vanished and surface water became memory etched in rock. The other endured a violent climatic convulsion measured in hundreds of thousands of years, yet retained its oceans and air. The contrast between Mars and Earth rests not in the absence of crisis, but in the tempo and structure of planetary change. Mars began its transformation early. Geological evidence indicates that ancient valley networks and delta deposits formed under conditions far wetter and likely thicker in atmosphere than those of today. Over immense spans, however, the smaller planet cooled more rapidly. Internal convection weakened, volcanic activity declined, and the global magnetic field disappeared. With diminished gravity and no sustained dynamo, atmospheric particles became increasingly vulnerable to solar wind stripping. Gradual loss of gases, especially lighter ones, reduced surface pressure. Without sufficient pressure, stable liquid water could no longer persist broadly at the surface. The transition was protracted, unfolding over billions of years, yet its direction was steady. Earth's late Permian crisis followed a different pattern. Volcanism intensified dramatically for a geologically brief interval, releasing vast quantities of carbon and sulfur compounds. Atmospheric composition changed swiftly. Temperatures rose, and ecosystems faltered. Oceans lost oxygen, and chemical balances shifted. Yet, despite the severity of these shifts, the structural foundations of the planet remained intact. Earth retained its magnetic field, its greater gravitational hold, and an active interior capable of renewing atmospheric constituents through continued outgassing. Planetary mass plays a decisive role in this divergence. Earth's stronger gravity reduces the rate at which atmospheric molecules achieve escape velocity, even under heating. Mars, with roughly one-tenth Earth's mass, cannot bind gases as effectively. Over time, cumulative losses alter climate irreversibly if not counterbalanced. Earth's more substantial internal heat budget also sustains plate tectonics, enabling the long-term carbon cycle to function as a regulating system. Subduction recycles carbon, while silicate weathering draws down excess atmospheric carbon dioxide over extended intervals. Mars, lacking comparable tectonic cycling, does not possess an equally robust mechanism for atmospheric moderation. The temporal scale of disturbance further differentiates these worlds. Mars experienced gradual attrition with no strong global feedback to halt atmospheric thinning. Earth's crisis, though intense, remained embedded within feedback systems capable of eventual correction. Volcanic emissions declined. Chemical weathering accelerated under warmth. Ocean circulation adjusted as temperatures moderated. The biosphere contracted but did not vanish, and biological processes contributed modestly to atmospheric stabilization. In comparing these trajectories, resilience emerges from interconnected systems rather than absence of disruption. Earth underwent rapid destabilization, yet the very dynamism of its geology and interior energy supported recovery. Mars, shaped by smaller mass and geological quietude, followed a path where loss accumulated without comparable renewal. The difference does not diminish the gravity of Earth's past crisis. It highlights instead how planetary characteristics determine whether upheaval becomes transition or termination. Earth could rebound because its atmosphere was not only held by gravity, but sustained by internal heat, tectonic recycling, and feedback processes operating across vast timescales. Mars illustrates how, without those reinforcing mechanisms, atmospheric decline can proceed beyond the point where oceans and temperate climates endure. Carbon moves quietly through Earth's systems, rarely noticed yet constantly exchanged among air, water, rock, and living tissue. It resides in limestone cliffs, drifts invisibly as gas, circulates through forests and plankton, and sinks into sediment far below the ocean floor. During the crisis of the late Permian, that circulation accelerated beyond its usual pace, revealing how finely balanced the cycle can be when perturbed abruptly. In its aftermath, the carbon cycle became not only a mechanism of recovery, but a lesson written in stone. Climate feedback systems shape how carbon behaves once introduced into the atmosphere. When greenhouse gases accumulate, surface temperatures rise. Warmer air can hold more water vapor, which itself enhances greenhouse warming, forming a positive feedback. At the same time, warming accelerates chemical weathering of silicate rocks, which removes carbon dioxide from the atmosphere over longer intervals. This weathering feedback operates more slowly than water vapor amplification, yet it exerts stabilizing influence across millions of years. The late Permian event demonstrated how rapid carbon release can overwhelm these stabilizing mechanisms temporarily, pushing climate into extreme states before long-term processes regain influence. Long-term climate regulation depends on the interplay between volcanic input, biological productivity, ocean chemistry, and tectonic recycling. Carbon buried in marine sediments may remain isolated for vast spans until subduction and metamorphism return it to the mantle, where future volcanism reintroduces it to the atmosphere. This geological exchange functions as a thermostat with a delayed response. It is effective not because it prevents change, but because it prevents indefinite escalation. When perturbations subside, the cycle draws atmospheric composition back toward equilibrium. The biosphere's sensitivity to rapid carbon injections reveals another dimension of the lesson. Life adapts, yet adaptation requires time. During the Permian crisis, rates of carbon input appear to have been fast relative to evolutionary turnover. Ocean acidification, warming, and deoxygenation progressed more quickly than many organisms could accommodate. The result was widespread extinction and simplification of ecosystems. Recovery unfolded only after environmental parameters stabilized within ranges tolerable for complex metabolism. The contrast between rapid disruption and slow regulatory response underscores the vulnerability of biological systems to accelerated change. Geological time stretches beyond human perception. Processes that restore balance may require millions of years, while the triggering disturbance may unfold over tens of thousands. In deep time, this difference is meaningful. Stabilization occurs, yet not on the timescale of individual generations or even civilizations. The rock record compresses these intervals into thin layers, but within those layers lie spans longer than recorded history. The carbon cycle operates faithfully across epochs, yet its corrective arc is patient rather than immediate. From this perspective, the late Permian crisis illustrates both fragility and resilience. The planet possesses mechanisms capable of rebalancing atmospheric composition, but those mechanisms do not shield ecosystems from interim upheaval. Climate feedback systems can amplify or moderate change, depending on scale and duration. Long-term regulation emerges from tectonics, weathering, and burial, not from instantaneous correction. The carbon cycle thus reveals a dual truth. It affirms that Earth is not destined for permanent destabilization from a single perturbation, yet it also shows that rapid alterations can exceed the adaptive capacity of living systems. Stability exists, but it is maintained through feedbacks that unfold across immense spans of time, reminding us that the resilience of planets does not guarantee the resilience of every life form that depends upon them. The Permian crisis was not the only moment when Earth approached the edge of environmental transformation. Across far older chapters of geological history, the planet has moved toward extremes that might have seemed irreversible. Each episode unfolded under different boundary conditions, driven by distinct mechanisms, yet together they trace a pattern of stress followed by rebalancing. The record preserved in ice ages and thermal pulses reveals that instability is not foreign to Earth's system, only variable in magnitude and duration. More than 600 million years ago, during intervals often described as snowball Earth, global glaciation may have extended from pole to equator. Geological deposits of glacial origin appear in paleolatitudes that suggest near tropical ice coverage. If oceans were largely sealed beneath ice, the planet would have reflected more sunlight, amplifying cooling through high albedo feedback. Such conditions appear severe enough to challenge photosynthetic life and disrupt marine ecosystems profoundly. Yet even this deep freeze did not persist indefinitely. Volcanic carbon dioxide accumulated in the atmosphere over millions of years, unable to be removed effectively by weathering beneath widespread ice cover. Eventually, greenhouse warming intensified, melting ice and restoring open water. The cycle demonstrates how feedbacks can shift from amplifying cooling to amplifying warming, leading ultimately to escape from extreme states. In contrast, the Paleocene-Eocene thermal maximum, approximately 56 million years ago, represents a rapid warming interval driven by a large carbon injection into the atmosphere and oceans. Isotopic excursions in marine sediments indicate a substantial addition of isotopically light carbon, likely from methane hydrates, volcanic sources, or both. Global temperatures rose several degrees within a geologically brief span, and ocean acidification stressed marine organisms. Terrestrial mammals exhibited shifts in body size and migration patterns. Yet, as in the Permian, silicate weathering and carbon burial gradually reduced atmospheric carbon dioxide, allowing climate to stabilize over subsequent hundreds of thousands of years. Other near catastrophes are recorded in mass extinctions and anoxic events dispersed across the Phanerozoic. Ocean chemistry has tipped toward oxygen depletion multiple times. Continental configurations have altered heat distribution. Volcanic provinces have reshaped atmospheric composition. None of these events left the biosphere unchanged. Each imposed filters through which only certain lineages passed. Recovery did not restore previous ecological structures exactly, but it established new equilibria shaped by the survivors. A pattern emerges when these episodes are viewed together. Perturbations often arise from imbalances between carbon input and removal, or from shifts in albedo and circulation. Feedback systems amplify the initial disturbance, driving climate toward extremes. Over longer intervals, counteracting feedbacks, including weathering, burial, tectonic recycling, and biological processes, gradually moderate conditions. The planet oscillates within boundaries defined by energy balance, gravity, and solar input. This pattern does not suggest inevitability of comfort or uniform outcomes. The durations of extreme states can span millions of years, and biological losses can be immense. Yet, Earth's history indicates repeated crossings of thresholds, followed by reconfiguration rather than terminal collapse. Snowball glaciations yielded to greenhouse escape. Thermal spikes receded under chemical drawdown. Extinction horizons gave way to diversification. Through these deep time experiments, Earth reveals a capacity to endure states that appear, in isolation, insurmountable. Instability punctuates its history, but so does recalibration. The cycles of near tipping and gradual recovery form part of a broader narrative in which planetary systems explore their limits without permanently forfeiting habitability. Balance on a planetary scale is rarely obvious. For long intervals, climate seems steady. Oceans circulate with familiar rhythms, and ecosystems weave intricate patterns that appear enduring. Yet beneath this apparent constancy lie thresholds that, once crossed, reorganize systems rapidly. Stability is not the absence of change, but the maintenance of feedbacks within certain bounds. When those bounds are exceeded, responses can accelerate in ways that are not proportional to the initial disturbance. Tipping points arise when gradual forcing pushes a system past a critical threshold, triggering a shift to a new state. In climate dynamics, these points often involve feedback loops that amplify change rather than dampen it. Ice reflects sunlight, so expanding ice cover increases albedo and promotes further cooling. Conversely, melting ice exposes darker surfaces that absorb more heat, reinforcing warming. These processes are nonlinear, meaning the outcome is not a simple continuation of prior trends. Instead, the system can pivot abruptly once internal feedbacks dominate over stabilizing influences. During the late Permian event, multiple components of the Earth system moved toward such thresholds simultaneously. Greenhouse gas accumulation warmed the atmosphere. Warmer oceans held less dissolved oxygen. Reduced oxygen altered marine chemistry. Altered chemistry affected biological productivity. Each factor interacted with others, creating cascading effects that exceeded what a single variable might produce in isolation. Nonlinear responses transformed incremental carbon increases into widespread ecological disruption. Planetary systems are fragile not because they lack resilience, but because resilience depends on interconnected feedbacks functioning within constrained ranges. The atmosphere, oceans, cryosphere, lithosphere, and biosphere operate as coupled subsystems. Changes in one propagate through the others. A modest alteration in atmospheric composition can influence ocean circulation. Altered circulation can shift nutrient distribution. Nutrient shifts can modify biological activity. Biological changes can, in turn, affect carbon cycling. The complexity that enables self regulation also creates pathways for amplification. This fragility coexists with long term stability, producing the illusion of permanence. Human timescales are brief relative to geological rhythms, so gradual drift can appear static. Mountain ranges seem immutable, coastlines fixed, climates reliable, yet sedimentary records reveal repeated reorganizations of Earth's surface and climate. Tipping points are not daily events, but neither are they rare in the context of billions of years. They are inherent features of dynamic systems, governed by feedbacks and energy balance. The distinction between stability and collapse often lies not in magnitude alone, but in timing and interaction. A perturbation introduced slowly may be absorbed through adaptive feedbacks. The same perturbation introduced rapidly may overwhelm those feedbacks before they can respond effectively. Nonlinear behavior ensures that effects cannot always be predicted through simple extrapolation. Past crises illustrate that once certain combinations of temperature, chemistry, and circulation align, transformation can proceed with surprising speed. Understanding this thin line does not imply inevitability of catastrophe, nor does it guarantee safety. It highlights that habitability depends on maintaining feedbacks within their operating range. Earth's history demonstrates both its capacity for abrupt shifts and its ability to find new equilibrium afterward. The boundary between those states is not wide, and it is shaped by interdependent processes that respond collectively rather than independently. Within that narrow margin, planetary stability is sustained, yet always contingent upon balance rather than permanence. After upheaval reshaped oceans and continents, what remained was not a lifeless sphere but a planet still in motion, still cycling elements, still turning beneath its star. The same forces that had amplified instability now provided the framework for endurance. Weathering continued to draw carbon from the air. Plate boundaries persisted in their slow rearrangement of crust. The magnetic field maintained its silent guard against solar wind. These mechanisms did not prevent catastrophe, yet they preserved the structural integrity required for renewal. Resilience on Earth is not a single safeguard, but a network of processes operating across scales. The carbon cycle moderates atmospheric composition over immense spans. Ocean circulation redistributes heat and dissolved gases, sustaining habitable gradients. Tectonics recycles materials and exposes fresh rock for chemical reactions. Even biological systems contribute through photosynthesis, respiration, and organic burial, shaping atmospheric chemistry with each generation. When perturbations exceed normal ranges, these systems may falter temporarily, yet their continued operation makes recovery possible once extreme forcing subsides. From this resilience emerged innovation. After the Permian extinction, evolutionary pathways diverged in new directions. Surviving lineages explored ecological roles left vacant by vanished competitors. Novel body plans and metabolic strategies appeared over successive generations, reflecting selection within altered environments. Reptilian groups expanded into niches that would eventually yield dominant clades of later eras. Marine communities reorganized around new assemblages, reconstructing food webs from simplified beginnings. Innovation did not erase prior loss, but it transformed emptiness into opportunity. Chance also played a quiet yet decisive role. Survival during mass extinction often depends on traits that happen at a particular moment to confer advantage. Geographic distribution, ecological flexibility, and random variation influence which lineages persist. A species occupying a sheltered microhabitat or possessing tolerance to temperature extremes may endure while others perish. Over time, these contingencies shape the trajectory of evolution. The world that followed the Permian crisis was not predetermined. It emerged from a combination of structural resilience and the unpredictable filtering of life through stress. The continuity of life across such thresholds appears improbable when examined against the magnitude of disruption. Oceans grew hostile, climates veered toward extremes, atmospheric chemistry shifted, and vast percentages of species disappeared. Yet microbial communities endured, photosynthesis continued in sunlit waters, seeds and spores survived in soil and sediment. These threads were slender, yet sufficient. With time and stabilization, they multiplied, weaving new ecosystems atop foundations laid by survivors. Earth survived not because it avoided crisis, but because its systems retained capacity for adjustment. Gravity held the atmosphere. Tectonics sustained long-term carbon regulation. Biological processes responded to renewed opportunity. The planet absorbed immense shock and then, gradually, recalibrated. In this endurance lies a quiet testament to planetary resilience. Catastrophe redefined conditions, but it did not terminate habitability. The improbable continuity of life across deep time reflects both structural safeguards embedded in Earth's physical systems and the adaptive potential of living organisms. Together they allowed a world that nearly unraveled to persist, altered yet alive, carrying forward the possibility of complexity long after the shadow of extinction had passed. There was a span in deep time when warming accelerated, oceans stagnated, toxins spread through water and air, and ecosystems unraveled at a planetary scale. The cascade unfolded through interacting feedbacks, each intensifying the next, until much of the complex life that had flourished for millions of years disappeared. In rock layers and isotope ratios, The imprint of that descent remains clear. It marks a threshold approached through heat, chemical imbalance, and biological collapse. And yet, Earth did not follow the trajectory of a barren world. It did not shed its atmosphere into space over eons of erosion. It did not evaporate its oceans into a vapor that could never return. The magnetic field endured, gravity held firm, plate tectonics continued its slow circulation of elements, and silicate weathering waited patiently to draw excess carbon back into stone. Beneath surface turmoil, deeper systems preserved the structural framework of habitability. The oceans warmed and lost oxygen, but they did not vanish. Liquid water persisted across the globe, anchoring climate and chemistry even at their most unstable. Clouds formed, rainfall continued, rivers flowed, and sediments accumulated in basins that would one day reveal the story. The air thickened with greenhouse gases, yet total atmospheric mass remained sufficient to maintain pressure compatible with seas and life. These were margins rather than absolutes, narrow boundaries not crossed. The crisis brought Earth closer to planetary instability than many intervals before or since. Temperatures rose dramatically. Carbon cycled at rates that strained stabilizing feedbacks. Ecosystems simplified toward near emptiness. For long stretches of time measured in millions of years, the outcome was uncertain in its unfolding. Recovery required volcanic quieting, accelerated weathering, renewed circulation, and the patient reconstruction of food webs from microbial foundations upward. No single mechanism guaranteed success. It emerged from the convergence of interacting systems that remained just within reversible limits. Habitability is not a permanent entitlement written into a planet's existence. It is the product of balanced forces operating within constrained ranges. Solar input, atmospheric composition, internal heat, gravitational strength, and geochemical cycles must align closely enough to support liquid water and metabolic complexity. During the Permian crisis, that alignment strained under amplified feedbacks. The world tilted toward conditions that, if extended further, could have transformed it more profoundly. Earth's survival was therefore not inevitable. It depended on structural resilience embedded in physical and chemical systems, and on the persistence of living processes capable of adaptation once extremes receded. For millions of years, the planet hovered within a zone where stabilization remained possible but not immediate. Time itself became a factor, allowing slower feedbacks to counterbalance rapid disruption. When viewed across billions of years, the episode becomes neither a fleeting disturbance nor a terminal failure. It is a reminder that planetary systems explore their limits and occasionally draw near to boundaries that divide temporary upheaval from permanent loss. The narrow escape of the late Permian does not suggest invulnerability. It reveals instead a delicate equilibrium sustained by interconnected processes that can falter, amplify, and eventually recalibrate. In that long interval between collapse and recovery, Earth remained a world in suspension, altered yet intact. Oceans endured, air persisted, and life, reduced but unextinguished, carried forward the possibility of renewal. The fragility of that balance invites quiet reflection, not fear, but recognition that the continuity of habitability rests upon forces that must remain in careful proportion.